Happy Tuesday, campers, or I guess whenever you're watching this. Alright, so first we're going to start with just getting some notes in our comp book to review what we've been learning the past few days. Primarily, we learned how to graph quadratic functions in vertex form. So, quick vocabulary, a quadratic function is a function where the highest degree of x is 2. So, the highest exponent that you have is an x squared. And where a, b, and c are real numbers. Also, a can't be 0. Remember that, because if a were 0, we would end up with a linear function. A parabola is the fun word that you guys love repeating in class, which is the U-shape graph that a quadratic function creates. A parent quadratic function is where we have f of x equals x squared. That's our parent quadratic function. The vertex is, well, let's go ahead and draw a couple of parabolas, at least as neatly as I can. What is the vertex? The vertex is that point or that point, right? How could we refer to that? This would be the lowest point, and this would be the highest point. So the vertex is the highest or lowest point of a parabola. We've also referred to these. This is the minimum value of y. This is the maximum value of y. We can refer to that point as h comma k if we're dealing with vertex form. The axis of symmetry, well, we know that if I drew these neatly, that if I had a line here, this side is going to be the same as this side, right? This side should be the same as this side if I had drawn decently. So the axis of symmetry is the vertical line through the vertex which the parabola reflects across. Vertex form is f of x equals a times x minus h squared plus k. hk, as we said before, is the vertex. H represents what? That's right, the translation that the graph would make horizontally. So it's the horizontal translation. K represents the vertical translation. And A determines what? Determines whether the parabola is stretched or shrunk. And also whether it is, if it's a negative A, it would be reflected across the x-axis. Another way to think about that table that we did before, let's just think about the absolute values of A. Whether A is positive or negative, if it's greater than 1. So if the absolute value of A is greater than 1, then what's going to happen to the graph? The graph will be stretched. And if the absolute value of A falls between 1 and 0, so it's a fraction, and we're just dealing with positive A's right now, it's a fraction, what's going to happen? The graph will then shrink. And if A is negative, what will happen? It will reflect across the x-axis. Easy peasy. Can't believe you didn't know any of this a week ago, huh? Okay, so now let's just, so we can get it in our notes, we're going to graph another quadratic function if it's given to us in vertex form. So we're going to graph f of x equals 3 times x minus 2 squared minus 4. So first thing to do is identify the vertex and plot it. Well, we know our h, which is the opposite of what it looks like. So our h is a positive 2 and our k is a negative 4. So our vertex is 2 comma negative 4. So let me very quickly create my grid, label my scale, and now I can plot my vertex. There it is, my happy little vertex. Okay, so we can either complete a table, or we can just think about what we learned before and something else that I'm going to teach you today. We can think about the value of A and then just plot points by moving over 1 and up a certain amount or down a certain amount. We could even do it again. We'll move over and up a certain amount or down a certain amount, thinking about A. The safer way is to complete a table. Nothing wrong with creating a table. But also think about the axis of symmetry to save yourself some time. So if I create a table, I know A equals 3. and I have x and y, well, if x is 2, I already know y is going to be -4 because that's my vertex, right? And I'm just going to go up from here just a few points. 3, 4, and 5. Now, because a is 3, I already kind of should be able to know if I went over 1, how far up I have to go. But let's go ahead and do the math. If I plug 3 in, I get 3 minus 2 is 1. 1 squared is 1. 3 times 1 is 3. Minus 4 gives me -1. And those of you who jumped ahead and said, I just need to go up 3, over 1, up 3, congratulations, you have got -1. And then 4, if I put 4 in, I get 4 minus 2 is 2. I end up getting 8. And if I put 5 in, I end up getting 23. And now I can plot those points. I'm going to go over 1, so to x being 3, and up to -4, or sorry, up to -1, and plot those 2 points. And I'm also going to plot these 2 approximate points just to help guide my parabola. And I'm going to, as neatly as possible, draw my parabola. Again, it is not a V. I'm not dealing with straight lines. I'm dealing with curves. Okay, so that was the review. But now I have some food for thought for you. And on your notes, it's a little more complicated than this. But here's what I'm going to show you. Now, if this clicks with you, great. If it doesn't click with you, keep using tables. Don't worry about it. Don't force it. One day, you're going to say, oh, and it's going to click. But for now, I'm just going to show it to you. And if you can use it, great. So let's start with our parent function. There it is. And actually, I'm going to, please pause here and go through this page and then come back and play. Hey, nice to see you again. All right, so here's our parent function. And what I want to think about is if I go from this vertex over 1, how far up do I have to go? We already did this. I go over 1, I have to go up 1. Well, what if I did it again? If I went over 1, how far up would I go? I'd go up 3. And if I did it again, I'd go over 1, and I would go up how many? I'd go up 5. This 1, 3, 5, if your A is 1, this is always going to be your pattern. I'm actually going to make a little table over here so I can keep track of it. If A is 1, then every time I go over 1, the first time I go over 1, I go up 1. The next time I go over 1, I go up 3. And the next time I go over 1, I go up 5. Just going to keep track of that. All right, let's move on to our next parabola that I've graphed for you. And here A is 2. And think about the same thing. If I went over 1, how far up would I go? I'd go up 2. And we learned that one already. But what would happen again? If I went over another one, how far up would I go? I'd go up 6. And if I went over another one and I went up, I ran out of graph. Let's think about what's going on here. The first time I went over 1, how far up did I go? I went up 2. What's the relationship here? What's the relationship here? The next time I went over 1, I went up 6. What's the relationship here? What's the relationship here? What do you think if my graph finished? How far up do you think I'd have to go? For my third time over, I'd go up how far? I'd go up 10. You see the pattern? And it's all based on this 1, 3, 5. Let's look at another one. Let's look at A equals 1/2. There's my parabola for A equals 1/2. Let's see if you can predict these before I do it. So if I go over 1, I'm going to go up instead of 1, I'm going to go up 1/2. And if I go over another one, I'm going to go up instead of 3, 1 and 1/2. And again, if I go over 1, instead of going up 5, I'm going to go up 2.5. Look at that pattern. Look at these, how these relate. 1 and 1/2, 3 and 1.5, 5 and 2.5, and look at how A relate. If you get it, you get it. If you don't, that's okay. Use tables. On to today's lesson. So now we're going to solve quadratic equations graphically. The essential question, how can you solve a quadratic equation by graphing? Here's a big hint. You're going to convert it to a system. Yay, systems! Don't you miss systems? Okay, So as a quick review or introduction, let's look at this system that we have graphed for you. This is an exponential function that you haven't seen before. This curve right there is f of x equals 2 to the power of x. Ooh, how would you solve that? And then this one is pretty simple. That one is g of x equals 4. And what's the solution to this system? That point right there, which is 2 comma 4. But what if instead of giving it to you as a system like this, I gave it to you as this equation, 2 to the power of x equals 4. Now, if you saw this as a math problem right now, you wouldn't know how to solve this. However, because I've graphed it for you, what do we have? We have that point right there. The value of x for that solution is, what is it? 2. So we know that for this equation, x equals 2. And we can solve that because we converted this equation to a system, graphed it, and there's our solution. So we're going to use that today. All right, so they've already graphed 3 quadratic functions for you. A is the graph of f of x equals x squared, so that's our parent function. B is the graph of f of x equals x squared plus 4, so it just translated up 4. And C is the graph of f of x equals x squared plus 8, so it just translated up 8 units. On the same coordinate grid, go ahead and graph the function g of x equals 4. So if g of x equals 4, then it's going to be 4 all along. There it is. That's g of x. What type of function is this? It's a constant function, and it is a horizontal line. At how many points does this graph intersect with each parabola? So how many times does it intersect with parabola A? There's one. There's one. It intersects twice. How many times does it intersect with parabola B? Ooh, you might not think it intersects, but there, right there, the vertex, it intersects 1. And how many intersections do we have parabola C? Never. They're never going to meet. We have 0. So if we had this system of parabola A and this line, how many solutions would we have? 2. If we had parabola B and the line as our system, how many solutions? 1. And how many solutions would we have with C and the line? 0 solutions, no solutions. Sounds familiar, doesn't it? All right, so we're going to use the graph to find the x-coordinate of each point of intersection of the graph of g of x and parabola A. We're going to show that each x-coordinate satisfies the equation x squared equals 4. So if we look at this graph and we're dealing with parabola A, then we have an intersection at -2 and +2. So we're going to say just plus and minus 2. And how can we show this? Well, we're going to plug that plus or minus 2 into our equation. Plus or minus 2 squared, does that equal 4? Yeah, -2 squared equals 4 and +2 squared equals 4. Yeehaw. And now we're going to use the graph to find the x-coordinates of each point of the graph of g of x and parabola B and show that each x-coordinate satisfies this equation. So here's parabola B. Where do they intersect? When x is 0. So x equals 0. That's the only solution that we have. And to prove that this really is a solution, we're going to plug in 0 into that. We'll have 0 squared plus 4. Does that equal 4? Yeah. How would we use exactly what we did here to solve this equation graphically? We would convert both parts of this equation. We would convert it to a system and we would graph it. So we would have f of x equals x squared plus 5, because that's the left side of the equation. We would also have g of x equals 7, because that's the right side of the equation. And we would graph it and we would find the x-coordinates of any intersections. And then those would be our solutions. Those would be our x values. All right. So basically what it's saying here is just a little note for you. You can solve an equation where you have vertex form equals a constant, which is called a quadratic equation, by graphing the functions f of x equals the left side of the equation and g of x equals the right side of the equation, and finding the x coordinates of each plot of the intersection. This is what your homework is going to be. There's only 4 problems, so I'm not going to show you an example. This is your example. So we're going to solve 2 times x minus 4 squared plus 1 equals 7. So first we're going to graph the left side of this. So we're converted that to a function. F of x equals, same thing. Find the vertex, plot the vertex. Let's go ahead and use our initial rate of change. We could move 1 left or right. And because a is 2, if we move 1 left, we're going to go up 2. If we move 1 right, we're going to go up 2. So we'd have these points, 3, 3, and 5, 3. And now with what I just showed you, we could also go over 1 and up 6, right? And plot those points. And I can very neatly graph that. Boy, does neatness matter right now. And now I'm going to graph the right side of my equation. I became a pirate, or I don't know what I became. Graph g of x equals 7. That's just that horizontal line right there. And how many solutions do we have? At how many points does they intersect? It intersects at 2 points, but oh man, that's going to be difficult to see, right? So we have 2 points of intersection. X is about 2.3 and x is about 5.7. These are estimations or approximations. Well, how can we find out if these approximations are reasonable? We're going to plug it in. So for each x value, we're going to find the actual value of f of x. So if we plug in 2.3 for x, we get 2 times 2.3 minus 4 squared plus 1. And that is equal to 2 times negative 1.7 squared plus 1, which is equal to 2 times 2.89 plus 1, which is equal to 6.78. And if we also plug in 5.7, that was the other approximation of x, we end up with 6.78. Are these equal to 7? Not quite. So we're reasonable, but these are not the actual values of x. So for that reason, our function values are not exact. Our solutions are approximations. They're approximate. I don't like the next question. Cross that off. But instead what I want to ask you is this. Could we ever, by solving by graphing, could we ever get exact solutions? And how would we know that they were exact solutions? If we could have exact solutions if the parabola and the line intersect at lattice points, at points where the lines of the graph intersect. For what value of c would this equation have exactly one solution? Think back about those 3 parabolas that you saw before. Well, it would have exactly one solution if c was equal to 1. Why? Because that would be going through the vertex. So it is the parabola's vertex is where the line is the value of the parabola's vertex. So that is when you're going to have one solution. Is when this value is equal to the vertex. Or equal to the y value of the vertex, I should say. All right, a real world problem. We are not going to do this whole thing. We are going to do part of it, though. So go ahead and read this. Pause and read that first part. And I want you to be able to write the equation that you would need to solve. Well, what are we doing? Well, we have this, the function that represents t is time in seconds, that gives us how quickly the performer falls. We have negative 16t squared plus 20. And, well, how far is the person falling? They started at 20 feet. We want to know how far is it till they hit the safety net. So we're looking for when does that equal 5. So that's the equation we're going to solve. And how would we solve that if we were to graph? And if you're really bored, by all means, go on to desmos.com or pull out your graphing calculator and solve this. But we're actually not going to. But I want you to think about what two functions would we write to solve this equation. We would write one function as y equals the left side, and we would write another function as y equals the right side. Graph these two. If they intersect, we have 2 or 1 solution. If they don't intersect, we have 0 solutions. So again, we're not going to do the rest of this page. And that's all for today, folks. See you in class.